everyone, we are going to chat about limit. Well, we already talked about limits. What we're going to talk about today in the 1.4 is we are going to focus on this idea of the derivative. So the derivative, let's chat about, I skip 1.3 a little bit because it really doesn't have, everything we kind of need is in this 1.4 section. So if you have not yet done so, what I need you to do is I need you to stop this video and I need you to look at page 78 in 1.3. Okay, and page 78 in 1.3 is going to give you an idea of what I'm talking about right now, because I'm going to talk about this pretty quickly because I want to get to some examples for you. So hopefully you just paused. You went out and looked at page 78 from 1.3, and now you are back. And let's talk about this idea of the derivative. So in 1.2, our whole discussion in 1.2 was this idea of finding, let me go ahead and make this an actual line, finding the slope of a curve, right, by using the tangent line. So that is what I'm going to do right here. I am going to, remember in 1.2 what we did was we actually just estimated that, and we weren't actually able to find, unless they drew the tangent line for us, we weren't really able to find the actual slope of that tangent line. So let's just say that I have some function that's maybe doing something like this. And without loss of generality, meaning, the discussion I have here today will still work if I'm not in the first quadrant. I'm in the first quadrant right now, but I don't necessarily have to be in the first quadrant for this discussion to work. I want to draw that a little bit differently. Still getting used to this drawing system. Okay, so there's my function. Sorry, that's a little bumpy. But what I want to talk about is how, let's pick an x value, okay, where I would like to find maybe the slope of this curve. So let me get a different color here. And let's say I want to find the slope of the curve at some x value, let's say right here. And we know from 1.2 that the slope of this curve is going to be the tangent line, right? I could even draw the tangent line here. Oh, that's the wrong thing. Let's see. I'm going to try and get this off. Maybe like that about, right? So remember we want the tangent line. Oh, that didn't work. We want the tangent line to be, it hits that curve in one spot, and we want to make sure that that line kind of mimics the behavior of the curve at this x value, so that if we zoomed in, right, if we zoomed in on this point, it would be hard to even distinguish the difference between my purple curve here and my blue line. So how do we find the slope of that line? Well, we know from, like algebra class that to find the slope of a line, what do I need? I need to have 2 points. So what I'm going to do is I'm just going to take another point out here, okay? And I'm going to say, well, this point is just a little bit more than x. So let's just say that it's x plus a little bit more. And that little bit more that I'm going to do is called h. So this distance right here, I define to be h. Okay, this distance right here is h. If x is 1 and h is 2, then I'm going to be up at 3. So if I look at the line, I'm going to graph a line through this point and the point I found here. Okay, and this line right here is going to be what I am going to use to estimate the slope of this blue line here, which clearly is not a good slope. Look at the slope of this line. This slope is negative. The slope of the yellow line is going to be positive. So I know it's not a good approximation, but it's going to at least get me there. Let's talk about for a moment what the coordinates are for these points. So if I look at the coordinate of this first point right here, the x coordinate would be x. The y coordinate would just be my function evaluated at x, right? That's how we get our y value. So I have x and the function evaluated at x. This coordinate over here, what is my x value? My x value is x plus h. correct? And so what is my y coordinate? Well, how do you find your y value? You just evaluate the function at x plus h, or at your x coordinate, where down here, this is my x-axis, this is f of x. Sorry, I should have defined that before. So this is my first point, this is my second point. Again, this is just my x, right? These guys correspond to each other, x plus h. This guy is my x, and then y values. So then the slope of this yellow line, I can approximate the slope of my tangent line with the slope of this yellow line. And what is the slope of this yellow line? It would be the change in my y values. Oh, it's thundering outside. I don't know if you can hear that. All over the change in my x values. So here's my x value. Remember, those two are friends, so they have to go first, minus x. And if we simplify that, look at what that becomes. F of x plus h minus f of x. My x's cancel out all over h. That kind of makes sense to us that it should be h. So remember, that's just what this distance is. So this right here is the slope of the yellow line for any h value. So I could take any point, a distance from x, and I could use this. This is what we call the difference quotient in mathematics. Okay, well, how could I get a better point? You're right, I'm pretending that you are talking to me. You're right. What if I wanted to find a better approximation of this tangent line right here? Well, what if you took a point that was closer now? What if your new h was smaller? So my new x plus h then, I'm just going to take this x plus h and I'm going to start moving it toward x. If I do that, notice, look at what my line is now. If you look at this line is a lot closer. Look at how this line is a lot closer to this blue line right here. Okay, and how could I get an even better approximation? Again, I'm imagining that you're talking to me. I'm hearing voices apparently. What is this right here? This, let's do a new x plus h. Let's get an x plus h that's even closer to the x that I care about. Maybe right here. It's going to start getting a little hard to see, but that's why I wanted to use the colors. And maybe I get something like that. Oh, that didn't work. I really do love that I found this shift key. Except I don't. Sometimes I don't know how to use it. All right, so there we go. So look at this white line, if you can kind of see that. Look at how close this white line is to the tangent line that I care about. And I know that line's a little crooked. But how could I get an even better approximation? I could get closer to x. And what is this doing? It's just taking, notice before, whoops, excuse me. Notice before, this h, right, was from here to here. It was quite large. Then I went smaller. Then my h was from, whoops, then my h was just from here to here, so there's my distance for h. And then I got closer to x, so that got smaller. The h got smaller and smaller and smaller. So look at what's happening here. That h is getting smaller and smaller. Well, what numbers get really, really small? Numbers that are going to 0, right? The closer I get to 0, the smaller my number is. And so that is what we're going to call the definition of the derivative. Okay, so I'm going to, what we need to do is we need to add in this little h going to 0. We'll write this down as a definition, and then I just want to do a couple examples for you and make sure I don't make this video too long. So let me clear this all out, and let's just start a new page here. Okay, so this is a definition. You should have this in your notes already, but I can't help myself. I'm just going to put this. So this is the derivative. Oh, this is so exciting. The derivative of f of x is given by. So this is, we are going to learn ways to do this a little bit easier. f primed of x, so that's the notation we're going to use. This primed right here tells us it's the derivative of the function. And then here's what we're going to do. We're going to take the limit as h goes to 0. We want that h to get smaller and smaller and smaller of the change in y. Look at people, this is just a formula for slope. That's just my change in y, right? As I get points that are closer to x, all over h. Remember, that's such the change in x. Sorry, that looks a little weird. So that's the definition of the derivative that you need to know, and we will be doing examples with the definition. We will also find a way where we can do the derivatives that make it a little bit easier. So let's do some examples here. All right, so the first example. Use the definition of the derivative to find, and I want to mention here too that what does the derivative give us? It gives us the slope of the curve at that point. Definition of the derivative to find the derivative of, I know I missed that. Let's start off easy. F of x equals x squared plus 1. Okay, so I want to use the definition of the derivative to find the derivative of this function right here. So the first thing that we know is we know that the derivative is equal to the limit as h approaches 0 of f of x plus h. And remember what the derivative gives you. I keep saying this, but I want my students to remember this. It gives you the slope of the curve. Another way to say that gives you the slope of the tangent line. Okay, so I'm going to do a little bit of side work here. And I know, what do I need? I need f of x plus h. So what does that mean? That means everywhere you see an x, what do we replace it with? X plus h. That's what that means to evaluate a function at something. Okay, so I'm just kind of doing this over here. What do I know f of x is? Well, that's just this guy, right? So I'm going to plug this guy in for here, and I'm going to plug this one in here. This is like a formula that tells you what order to do things in. Okay, so let's do that. All right, so I would have the limit as h goes to 0 of what was f of x plus h? That was x plus h squared plus 1 minus, be very, very careful with parentheses here. I don't need those type of parentheses. I'm subtracting more than one term. When you subtract more than one term, people, you need to put parentheses. Make sure you look at the fun sheet for this section. The fun sheet for this section will give you lots of examples on how to do this without me blabbing over them. So you can just look at how to do it. Also, please make sure you understand all of the examples in the book, or else if you don't understand them, you need to be contacting me. X plus h, quantity squared. How do we do that? We square it, right? So that means we take x plus h times x plus h. It's just my side work, which is x squared plus xh, that's the outside, plus xh plus h squared last. That's just foiling, that's all. And then I can combine these two terms to be two of them, 2xh. So here's what we got. X squared, oh, that's a different color. I like that. So x squared, x plus h quantity squared ends up becoming x squared plus 2xh. You must FOIL it. You may not square the x and square the h and call it good. That is probably one of the biggest pet peeves of math teachers everywhere, I have to believe, if you take that squared across. You should come, if you are ever on campus, I have a funny cartoon about that. I don't know if you think it's funny or not, but now let's see if we can simplify a little bit. So I can cancel these guys. I can cancel these guys. Notice how I cannot take the limit yet because I have an h in the denominator. Okay, but what do you notice each term has left in it? Has an h. So the key to these is if you do these correctly, well, you can make a lot of mistakes and still think you're doing it correctly, but for sure one thing that has to happen is everything that's left must have an h in it. So if you notice here, I just factored an h out of this term. That gave me 2x. I factored an h out of this term. That gave me h. And now the glorious thing is that these h's cancel. So look at what we have. I have the limit as h approaches 0 of 2x plus h. So let's evaluate this limit. What happens to 2x as h goes to 0? Well, it doesn't care what h is doing. There's no h in it. So that just leaves us with 2x. What happens to h as h goes to 0? It goes to 0. That was kind of a redundant question. So look at what we have. This, my friends, is the derivative. What does this do for you? Well, if you want to find the slope of the curve at any point or any x value, so let's say I wanted to find the slope of this curve when x is 1, I would plug in 1 and I would get 2. I kind of talked about this a little bit in 1.3, but that's what that means. So if I wanted to notice, wow. Well, actually, I'll let you look at those examples. I want to do one more example for you. Let me clear this out. So I hope that makes sense. Okay, so I want to do the same thing. I'm not going to write out the whole thing, use the definition, blah, 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 but let's do the same thing with, let's say f of x equals 1 over, how about 2x plus 1? Okay, I want to find, I'll do this example and then we're getting a little long on this video, so if you're still with me, congrats to you. This may be a 2-pager. So I want the limit as h goes to 0 of 1, I want f of x plus h. So what does that mean? That means everywhere I see an x, I'm going to put x plus h. There's my f of x plus h minus f of x. This is just the definition of the derivative, people. Definition of the derivative all over h, okay? There's my f of x plus h minus f of x all over h. This one's a little tricky to see what to do. Anytime on our other one, when we had that squared, we just squared it and we FOILed it out. On this one, because we have fractions, what we need to do is we need to get a common denominator. So I'm going to get a common denominator. You all remember how to do that, I'm sure. This one needs to be multiplied by the denominator of this. I'm going to go ahead and take the 2 through. So that will be 2 plus 2h plus 1 on the top and the bottom. 2x plus 2h plus 1. And then what does this guy need? It needs this denominator. So this one is going to get 2x plus 1 all over 2x plus 1. Okay? And then let's continue on here. So give yourself plenty of room to do this. You could write this h on the bottom if you wanted to write as 1 over h everywhere else, you sure could, but I'm just going to leave it for right now. So what does this fraction become? That becomes 2x plus 1, right, on the numerator, minus this whole numerator here. So I'm going to go ahead and take the negative through. Please make sure you take that negative through. And then because they have the common denominator, I can put them all together. I'm not going to FOIL this denominator out because I know h is eventually going to go to 0. So I don't need to FOIL that out. And this is all over. Ooh, those were pretty good lines, if I would say so myself. All over h. So notice what happens here. Wonderful things, really. These guys are gone. Look at that. And these guys are gone. Okay, and if you remember anything, this is, if you remember anything about dividing by fractions, what do you do with a fraction? You flip it and multiply. So I actually could write this guy right here as 1 over h, just so it'll be a little easier to see what we can cancel here. Notice how I'm writing my limits still because I have not actually taken the limit yet. So limit as h goes to 0. Now what am I left with on top? A negative 2h. What am I left with on bottom? Let's not get lazy. Let's just rewrite it. Our hands won't fall off. It'll be okay. You know, a good mathematician is lazy, but a good mathematician is thorough before being lazy. And now, what do you notice I can do? Yep, I can let those h's cancel. Just because of time, because we're getting to about 20 minutes, and I feel like I'm getting toward the end of your attention span also. If I get rid of those h's, now I can let h go to 0. Because now when h goes to 0, all that happens is that that guy goes to 0. That's it. So what are we left with? We are left with on the top. Now I do not write the limit sign because I'm done writing. I'm done with taking the limit. What do I have on bottom? Notice I would have 2x plus 1 times 2x plus 1, which is all, so this is all over 2x plus 1 quantity squared. And that, my friends, is the derivative. And again, what does the derivative give you? It gives you the slope of the curve, which is also the same as the slope of the tangent line. Thanks for hanging in there with me. And when we move to the next section, I'll tell you we are going to find a much easier way to take derivatives of functions. We will not have to go through all this. The other example you need to watch that I did not do on this video is one involving radicals. So square roots, please look at that in the book. And email me or call me if you have any questions.